let's begin. So it's example time. That's what we'll be doing for the next for the next few hours, I guess, right? So we have a bit of an extended break, but I just want to just cover all the crux. Okay, so example 6.3. This is a warm-up example. What I want to show you, what must be in your head. I wonder if you have your formula sheet next to you, but the formula in question is this. This you should remember anyway by heart. This guy I want you to remember. That should be your bread and butter for the next few weeks. Okay, so what are they saying there? A horizontal cross compound steam engine develops a power at 30 kilowatt at 90 RPM. Remember what I mentioned to you? Typically, you're always given the mean speed, and this formula works with the mean speed. The coefficient of fluctuation of energy is found to be 0.1, which is going to be this guy over here. No, I'm lying. It's something different. The fluctuation of the speed is kept between plus or minus 0.5% of the mean speed. Find the weight of the flywheel if the radius of gyration is 2 meters, right? So, okay. First thing is first. Seems a bit strange, right? Now, what we need to do, just get my textbook here with me. We have to find, obviously, we want to check what we have here. The fluctuation of energy, delta E. Remember, delta E, that's another metric I'm going to put here. Where is my delta E? I'm going to find it for you so you can, I'm just putting it there so you can actually just see it. I'm going to copy this as well. This is like a basic mathematical problem, which is very uncommon in terms of assessment, but yeah, just showing you so that you know. So, what they're saying is that CE is 0.1. So CE looks like this. And that's the maximum fluctuation in energy, which is an E, change in E, and the work done per cycle, right? Okay, cool. So work done per cycle. So how do we write that? So work done, work cycle, right? Okay. So obviously, we have the radius. We're looking for the mass. We need to find this now. Omega we have, which is the mean speed, and in CS we also have, it's basically over here, which I talked to. Right. So let's find our delta E, which is the maximum fluctuation of energy. So CE is given as 0.1. We don't have delta E, and we have to find our work done per cycle. And to find a work done per cycle, as you can see there, work done per cycle is going to be, it's not going to be a 2 pi, blah, 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 blah. Rather, it's just basically a number of working strokes per minute. And this is very important also in compressors, you'll see. So your work done per cycle is basically your power times 60 divided by N. Basically just making this into RPM basically. Or alternatively, if you want to look at a better way, think about its power divided by N over 60. All right, so let's quickly just get this work done per cycle. So that's 300 kilowatts. And so remember this, I'm just making you aware of these different metrics. CE, CS, you're going to see 90 over 60. And remember, this is the work done per cycle. It's not the complete work. It's for every cycle. So how much do we get there? What's my work done per cycle? 90 is 90 divided by 60. Yeah, there we go. Did someone just get me that value? This is more of a warm-up problem. Yeah, making you guys aware of you know of just the metrics. Really. Then obviously we'll do the normal test level, exam level stuff just now. So you should get 200, but it's work done per cycle. That's, you could have it in joules rather. Right? It's not in kilowatts or anything. It's not per second. Right? That's why there's no speed attached here. Not speed the E speed here is per second, but it's essentially your work done per cycle. We're just gonna call it 200 to the power 3 Newton meter. You'll just adopt this unit for the work done per cycle. Obviously, this is the work per cycle. 200 kilonewtons per cycle. Right? That's how much work is being done. All we do, we take this guy, put it in here, and let's get our coefficient. Let's get our maximum fluctuation of energy. That should be easy to do as well. The unit's going to stay the same. Just keep a Newton meter. Obviously, that's going to be simple, right? That's 20 times 10 to the power 3 Newton meter. Guys, I highly recommend you follow this kind of stuff, because all this small stuff is going to come up. And once we have delta E, we have this now. So I can just quickly remove this. We've matured now, we don't need that. Ground up a bit. CS, what is my CS, guys? Who can tell me? Why is it 1? 1.
Yeah, because it's plus or minus, so it's minus 0.5 and then plus 0. So if you add them to, your range is like 1, I think.
Yes, that's 100% right. Yeah, I know, it's spot on. So Mr. Man is correct. So guys, if you ever see a plus minus in terms of your fluctuation of speed, it's not your CS, and it's essentially 1%. If you want to think about it, what it's saying is that if this is your mean speed, I'll just explain more clearer. But obviously, you don't have to be a rocket scientist, but this 0.5, 0.5, obviously it's plus and negative. The speed will fluctuate. Obviously, it's 0 here, 0.5 plus 0.5, and I can only fluctuate by 1%. Obviously, but 0.5 above, 0.5 below. So what it really means is that your CS is just 1%. That's really what it really means. And of course, 1% is 0.01. So making aware, if you see plus or minus, because I have a question here where they say it should not vary more than 1% of the mean speed, and if it's not 2%. In this case, it's just 1%. But either giving you plus or minus, it's just up or down essentially, right? And then once we have this guy also. Now we just have a plug and play thing. So typically we always want to stay in the Newton meter realm, not go to and not head to joules. But I will not fault you for units, for like these weird units, you know, just a conventional one. So we find the mass of the flower, which is the typical thing which I mentioned you're going to do. We're taking R squared, which is ratio gyration. So remember, this is also I, which is your mass moment of inertia. Anyway, so R was 2 squared times omega is always at your mean speed. Obviously, that's in RPM on radians, so we have to convert that guy. And your CS 0.01. So guys, remember, if it's plus or minus, it's essentially just times by 2. You know that it's 1%. It can't fluctuate more than 1%. All right. Can someone just quickly compute that answer for me? Like I said, guys, I highly recommend working through the stuff. You can only reap benefits from this because you are writing next week on this. So just the 2 chapters you're writing on. So 5628.95. That's a massive flywheel. Does it value actually make sense for that amount of a 300 kilowatt engine? That's kind of ridiculous. Did everyone get that? Is everyone on the same page there? Besides Mr. Manus, obviously he's given the answer.
Yeah, I got the same, sir. I got the same.
Fantastic. So what's important is that formula there, right? Is that formula on your formula sheet? Thank you, Mr. Doyle. So what's important is that formula because you'll be using that formula the whole time. Like I said, it's just a start, still a real warm-up. Towards another example I have here, small one, and if you want a solution, all over here again, we can just actually the same stuff. Example 1.2, maybe if you want. Yeah, working out that. Yeah, that looks like a better mass. Same kind of setup here, right? But you're always going to end up looking for the mass on the flywheel and the dimensions. That is for the test and for the exam, right? The reassessment, yeah, you'll see the reassessment stuff you go pick up. You know what will be in the reassessment. It's not difficult, but yeah, it's always the reassessment. So now we can finally start on where we need to be. So this next 2 examples, in fact, the next 2 examples forms 60% of the knowledge you require for energy systems. If you can do this 100%, you get 60% of the marks for this section. And it's always going to be within this realm. So I'm making you aware now that this is, if you're sleeping now, wake up and get in the groove now, because this is what we're going to be we're going to probably plan to do this 2 examples, take a break, or I might do 3 and then take a break and then just continue like that. Yeah. So we're just going to be, it's quite nice now, we're just going to continue solving. And the reason why I'm doing this so that I know you guys have more than enough practice. And obviously examples teaches us a few things here and here. But if I don't get to all of them, that's also perfectly fine. Okay. So here we go. Right, let's see the start of energy systems really. So what's important here is, let's read. So they're saying the turning moment for petrol engine is drawn to the following scales. Get familiar with this. Turning moment 1 millimeter equals 5 Newton meter. Crank angle is 1 millimeter equals 1 degree. All right, we'll get back to that. Park that for now. They're saying the turning moment diagram for repeats itself at every half revolution of the engine, and the areas above and below the mean are taken as 295, 265, 40, 340, and 270. So I'm just trying to figure out what is above and what is below. To the refer to figure here. 295. Yeah, anyway. So typically, with a question like this, I will surely give you a figure coupled with this, because I don't know why they didn't give you a figure for this one. So the figure would be, let me just go get it for you. So your exercises might not be like this, which is quite strange on the back of the textbook, but have a look. But I did post a whole another chapter from a textbook, which I found which will be very useful to you guys. But the idea is this, right? This is what we're looking at. Okay. Remember that multi-cylinder diagram I'm talking about? That's what we're going to be looking at. So the approach is, I normally work with a table, and what I mean by that, I'll show you now. Say point. Let's just see now. Very, very nice example. Like I said, it's test level as well. Sorry, so I have a table. Just to give me from a table. Say point. And copy my table as well. Point and what's this called again? And energy, right? You could call it point and energy if you want. Okay. Okay, Mr. Doyle, I hope to hear you on this one. So obviously we have points going from A, B, C, D to G. So we have A, B, C, D, E, F, G. Yeah, you get 2 marks for each of these things depending. I'll show you now. So what's our first assumption, which is always a standard, that we say A equals the total energy. We're referring to the total energy. We're not referring, let's call it E prime, right? Whatever. Let's just call it E prime. We're saying that the first point is equal to the whole diagram basically, or each individual part. So you'll see what I mean. Right? So let the total energy at A equal E. I don't know what is point E. Really, I think I'm really not sure what they mean by that, but from what I understand, I don't know if you guys have a bit interpretation. I don't know why in particular. Maybe it's because it's repeating itself. It's one full cycle, I'm assuming. I think that's the reason why. Is that because it repeats itself every half revolution? I'm not particularly sure why. But you're always going to say A equals E anyway. So I'm making you aware, or it makes no difference. I'm not sure why they've adopted this notation. So let's look at B. So at B, how do we start? We say A plus 295. Reason why plus, we've got a positive area there. At point B, we look at everything to the left, right? So we at point B, right? Do we say it's A, which is that, plus 295. Then at C, Mr. Doyle, can you please tell me what C is? Just by using pure logic here. It's A plus 295 and
Would it be minus 685?
Beautiful, done. Plug and play. There we go. So can I just get the what's plus 295 minus 685? Quickly, just work it out. Oh, it's not A, sorry. Yeah, it's A is fine. Yeah, what is it?
So 390.
Yeah, 390. So 390, positive 390. No, negative 390. So sorry guys, so I don't use A here, but A also equals E obviously, but I just want to keep it uniform in the textbook. You could have used A as well, but the idea is that they're just calling it E. So A equals E, just bear with me. Yeah, so just know. So it's E minus 390. What I'm making you aware of here is that you get a mark there already. So you're gonna mark, you need a mark for each, basically each one. And it's literally very easy. There's no complicated math yet. So for D, you follow the same thought. Obviously, I'm going to say E minus 390. And then, so where are we now? We had D. So what do we do now?
Plus 40.
Plus 40, exactly. Obviously, that's easy. We end up with the energy minus 350. Another mark for you in the bag. We do it at E as well. In this case, it's going to be E minus 390. We're E, right? We're adding 340 again there. Am I correct? Is it minus 340? So that's minus 340. So we're at point E. Everything to that side. Just going to add that. We should get E minus 690. In E minus 690. What can I check now? Mr. Kiefer. Let's see. Tsepo, Silas, what is next? E minus 690. What do we do now? What is next? What at point F? What do we do now?
270 plus 960.
Yep, plus 960, right? Plus 960. E minus E plus 270. And at the end, at G, what you're going to find is that this is how you know you're correct. So you have E plus 270 minus 270. And you're going to find out that this is going to be essentially E at this particular point. Or this must become 0. I'm telling you now, if this is not 0, if you don't come back to home, that means you failed something. And you'll get a mark probably for that as well. So it's 1, 2, 3, 4, 5, 6 marks. These questions are typically 15 to 20, depending on the question. Right, so then you can see how much marks that is. So I'm making you aware that if you're not going to come to 0 here, you made a mistake. It must cancel. You must have plus 270, and then eventually it'll minus the loss value. So that is stock standard for the multi-cylinder stuff. Please. A question like this, so just for me to show you how I can change it. I can just change the speed. I can just change the values maybe. I can just change the scale. And yeah, Bob's your uncle. All right. So what we're doing is finding the fluctuation of energy. That's the next step. So deal with the fluctuation of energy. It's a maximum energy minus the minimum energy. So looking at this column over here. Column 3, the max, where is the max value, Silas? Do you see it? And I'm not talking about absolute values, I'm talking about actual values. What's the maximum energy? If it doesn't occur, are you having a look?
Is it at C?
Nope. It's at B plus 295, and the lowest one is at E. You see, plus 295, that's a maximum plus. It's bigger than 270, and the minimum, the lowest one is minus 690. Can we all see that? Make sure you can see that. Silas is giving up there, not saying anything. And what we have to do is simply say E plus 295, simple guys, minus E, E, what's this now? Minus 690. Obviously this becomes a plus, the E's will cancel, and you're left with 95. I don't know what this is, but the area, which is the area, so 95 millimeters squared, right? It's going to be stock standard like this. It's either a millimeter squared. Basically, it's that area we was talking about. So like I said, this unit thing, even if you write 985, I'm still happy. But we're going to have to convert now. Okay. I think this will be 2 marks, definitely. Or maybe it'll be, I'm lying to you, it might even be 4 marks because that's max, that's min, and then yeah, 2 marks for the answer, something like that. Yeah. So I mean, obviously that's simple. And either going to follow what you're going to end up with this. So remember the energy I mentioned to you, it's a particular area. So when we're heading back, we want to convert this area back into joules, right? And the way we do it is by looking at its scale. Because remember, at the end of the day, it's 1 millimeter and 1 millimeter. But obviously, we have to convert this into radians, right? So you can see it's millimeter squared. So what I'm saying, the millimeter squared is of two components. It's the torque times the angle in radians, right? So what they say there, it's going to be 5, right? All you must do is just take your 1 millimeter, so it's 5 newtons, whatever that was. That can change obviously. So that's 5 newtons, and then times it by your angle and just convert it. In this case, it's 1 degree, 1 times pi over 180. What I'm saying is this is the first millimeter. Remember, this is the area under the curve. That's the second millimeter, and then basically over 180. And if we take this, we times whatever that is. So we're just going to say, to get it back into joules, you're just going to say 985 times 5 times pi over 180. And if we do this, you should get an answer, which I'm not sure. Just check the book again. So what answer do you get for that? That answer, we'll put it in joules. You'll see the next question has a similar thing, so you'll get used to it as we move along. All right. 85, that's correct. Yeah, 85.957. Remember doing it last night. 85.957. That is your total fluctuation of energy. And then I'm not going to do it. I'll give you guys 3 minutes to do it. I'll copy the formula for you. The formula we just used now. If you remember, and I want you to find the rest for me. Gotta make you work a bit. Very important formula. Know it by heart. Once again, this also is another 2 marks for you. 1, 2. So remember what the question stated. It wanted, maybe I should move it over here. It wanted the mass of the flywheel. Determine the coefficient of fluctuation of speed. We have the mass, so the 1 CS within this equation. So how many marks is this already? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 marks. And obviously, this part will be the last 3 marks, 15. So I'm making aware how straightforward it is, really. The understanding is somewhat linked to this, but I really tried my best. I hope I really justify the section. So I'll leave. You guys can find CS. I'll give you a minute to 2. Please, everyone, please do it. I see Miss Jackie's still not on here. Answer, please. Mr. Gabriel, you've been quiet. Nati. Guys, people are asking for the link. I don't know what's happening, or they're not joining. Or...
So it's the 10th month of the year. If they don't yet know how to use Blackboard, then it's a error.
Yeah, you know.
And
I mean, the announcement was posted, and you guys even shared it in the group. I just feel for people, but yeah, no, it's right. As though it is, think it's 3% or something. I can't remember the actual answer. So let me just quickly see. I'll work it out here. No, I mean, people need to, I'm just thinking, you know, I mean, I get a ton of questions and you're like, didn't you, I said this, or, you know, I can't really be rude and stuff. One can be, but anyway, I don't know. So that's 36, just plug and play. The radius of gyration was 0.15. This is always at mean speed. What is mean speed again? 1,800. 2 pi. Guys, very important question. Make sure you know this for the second test and the final. And squared, and then you're gonna find CS. I'll just CS for this video. All right, let's see what the answer is.
Yes, sir.
Yes, boss.
So I just want to find out, this CS, do we leave it as at 0.298, or do we have to, like the previous question, it said plus minus?
No, it's
So do we
straight.
have to
Just
divide it on? So we leave it like that.
because it was 0.3%. Obviously, if one knows, it's like it's plus or minus. So don't worry about it. I want that's just a value. Yeah. Thank you for asking that. Yeah.
Okay, thank you.
Yeah. Just a straight value will be fine. So we get what? 0.00. Was it 2 zeros? Yeah. 2,98671. Obviously, we times that guy by 100, you get 0.3%. Yeah. But Mr. Manis is very provident, and what Mr. Manis is basically saying is that your maximum minimum speed actually shouldn't fluctuate. It's a plus minus kind of thing, but this answer is acceptable. Again, yeah, for this I'll probably just maybe give extra 2 marks, I guess. This is like that looks worth 2 marks. Yeah. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14 marks. Yes, there's a question. Or is it not a question? Okay.
Yeah. So
Yes.
can you just repeat for me that part of delta E, maximum energy minus minimum energy?
No problem.
Yeah.
No problem.
Thereby, I'm kind of confused there. I don't know.
Yeah. So, Chilas, we got a table over here. You see column 3, right?
Yeah. Yeah.
We're looking for the highest positive, right? And the highest positive will be the maximum one. So the two positive I see is plus 270 and plus 295.
No. Okay. Thanks.
Yeah, and the lowest negative, and obviously the lowest negative is no. I like when questions are asked in the right time. Thank you for asking. See, it's easy to talk about that. I think like this man is good. He's like finding the shear force really. I was gonna make that analogy something like the point. It's similar to that. And you find across different angles within the well, it's a multi-cylinder, but like at different crank angles. It is something like it. But guys, if we can do this, I'm telling you now, you're in a really good place already. It's not difficult. The stuff is, if you open the textbook and start paging, you start to see, oh yeah, it's not bad. Because what I'm trying to highlight there is this concept of maximum minus minimum. And obviously I'm making you aware exactly what I'm looking for with this kind of stuff. And you'll see what I mean by this. Okay, that's example 1 down. Well done. Let's move on to the next one. Right, start to enjoy this. Example 16.5. Mr. Doyle, hope you're here still.
Always, sir, always.
Yeah, I know. So similar again, in this case, what they're looking for, they want Mr. Nangolo, they want that what is this? They want yeah, I can see this is better. Plus 52 minus 12. This is what I was expecting, you know, like to look like this. I don't know why the other one was like we are the signs, you know. I mean, you know, but anyway. There's a scale again, it's the same setup, it's always the same. The difference is now they give you a fluctuation over there, plus minus 1.5, and obviously we are aware that's times 2, so the fluctuation is 3%. what they're looking for, Mr. and Minus, is that mass of that flywheel now. So that is the thing in question. So what I'll do for you, obviously, is just place a diagram for each side. So if you are given a question, right, what is very key, and let's say you have to plot. If I give a question like this, either I'll give the diagram or I won't give the diagram. It's simple. All you have to basically do is have an axis. Excuse me, I don't mean with a crank angle and torque, and we have our line like this. So it's plus 52, right? That's gonna be, it's gonna go from A to B. Oh no, it goes to minus now, but a bit bigger, right? Doesn't have to be to scale. That's C. That's 1, 2, 4. Then we're going plus 92. So don't worry too much about the shape for this one. So that's D. Oh no, we're at minus 140, right? I hope you guys are getting the concept here, right? 85, same story. And that's from B, which I forgot my alphabet, to F, and so forth and so forth. So if you get something, do not be shocked by this. At least you'll be able to sketch the graph. All right. We get into the good stuff. So this is so after this we'll be looking at more flywheel stuff. Obviously, I'm deliberately repeating a lot of the same stuff for very good reasons. So please don't waste my time and your time. So let's have a table again. I'm gonna give you guys 5 minutes to complete the table. All right. And if you wonder why I do this, is so that you have practice within the lecture itself, so that you use time efficiently and not, you don't have to squeeze in new knowledge. So what do we have as normal? We have our point and we have our energy, right? You can have just two tables if you want. I'm just deliberately doing the 3-1. You can literally just have your final answer here if you want. But guys, we have till H, so it's A, B, C, D, E, F, G, H. You can have till Z, just making away. Don't be shocked if it goes in forever. I'll give you to the Greek alphabet, just to kill the time. Again, we just start with the same thing, A equals E. And then now I want you guys to basically find each point by yourself using this diagram. All right. What's important, you want to reach home, you want to find out that A will eventually equal E here. So there will be no change, it'll be zero. There'll be zero when you, but in the end, you must have plus minus 107 plus 107, which will be equal to 0. So guys, I'll give you around 5 minutes, which is half past, then I will check in and just complete the question for you. But please do this, right? Ladies and gentlemen, now. This guy got the mesh already. It's crazy. Yep, that's definitely the spot on. Yeah, that's the exact answer which I got. The guys just get the energy. There is less. It took 3 minutes. No, it was 2 minutes. Just work through it. Welcome, Ms. Jack. I've been waiting for you. And I'm a Sambo. If you want to follow on your textbook, we are at page 575, doing example 16.5.
Sorry, sir, can I see the question a bit more, please?
Yeah, don't you have a textbook? Yeah,
Mm-mm.
or at least a PDF. Everyone get the mess? Okay, I gave you guys enough time there. So let's work through this one. Obviously just some people joined, and let's quickly see. So at B, so again we always looking at a point, and then looking towards the left. So at B, we know it's going to be E plus 52, right? Someone say something. No, it's not the first example. You joined late. And then at C, we're going to go E plus 52 minus 124. Right, and if you add those guys up, you should get E plus 72. And then a D, right, so we have E plus 72, and a D, we have got a plus 92 now, right? Simple. And if you tally that up, you should get E plus 20. So far, it seems like C has the maximum amount of energy with the Silas. It seems like so far. Anyway, so E plus 20, and then at F, we got a, now we're at E, so we have a minus 140. Obviously, that becomes E minus 120. So our maximum positive thus far is this guy, and our maximum negative is this guy. So at F,
So your
yes.
C is minus 2, not positive.
Yes, thank you very much. Thank you very much. Yeah, sorry. It's a slip of the, yeah. So it's E plus 120 at F. I'm at F, so it's plus 85. And that's E minus 35. At G, it's a minus 72, so it's E minus 35 minus minus 35 minus 72, and we're getting E minus 107. And like I said, in the end, I must all balance out. E minus 107 plus 107. You should just get E, which kind of just say that the energy in equals energy out kind of thing, yeah. Like a shear force or bending moment diagram. So Silas, can you please tell me my maximum energy and my minimum energy? Please.
That's 52 maximum, and
yep. Thank you.
And 120 minus minimum.
Beautiful. Thank you very much. So main energy. And of course, guys, these must cancel, like I said, and we have 52 plus 120, which will give you 172. And we call it what? Millimeter squared. Obviously, you know, millimeter squared, we call it millimeter squared, right? Yeah. And then, like I said to you, we convert this, we convert this into joules. And the way we do it, we look at our scale. All we have to say is 172 times 600. Get your angle. Your angle is 3 degrees. You convert that into radians. 3 times pi over 180. And you can get your maximum fluctuation energy in joules. Okay, this is the main procedure for these problems. For this particular type anyway. And is my thing right here? Oh, it's 180, sorry. You should get 5403.55 Newton meter or joules, right? Depends on the way you want. And Mr. Mantambo, we must check and find us. Where's it formula now? Where's our formula for coefficient of energy? I want to paste it. I just want to paste it for them. Bread and butter. the section. You're always going to end up here, guys. So what I'm making you aware of is so Silas, you work on our mass for us. They want to find the necessary mass to flywheel. You're always going to go through the whole diagram process, and in the end, you're going to end up with your maximum minimum fluctuation, and then you're going to have to work out some parameters here. Sometimes they'll give you each, they'll give you, depending on what they want, obviously, they'll give you different things, but this is the core of 50 to 60% of the actual content. Okay, in case no one wants to do it for me. So it's 5403.55 equal. Mass we're looking for, we've got the radius, which is 0.5 of the flywheel. Omega, that's obviously the mean speed of 600. You have to convert that into radians squared. And our coefficient of fluctuation, plus or minus 1.5%. Someone else besides Mr. Romanus, can you please tell me, let's say Mr. Mlonzi, can you tell me what is the speed? What's the fluctuation speed? The value? What is that value, please? Plus minus 1.5%. Are you thinking about it? Fantastic.
3%.
Yep, thank you. It's time 0.03. Right, we discussed that. Your mass will come out to 182.497. Guys, we can do this. Well done. And I really mean when I say that. So how do I mark this? If you have to do a diagram, you probably get 1 or 2 marks for it. So I'll just call it 1 now. Over here, I'll give you 1, 2, 3, 4, 5, 6, 7 marks, probably 7. Yeah, I'll give you 1, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah. Like I said, it's around 15 to 20 mark questions, typically. 3 marks. Certain things are complicated in the work, some certain things are not. Yes, Mr. Mantambo. Wandile Mantambo.
Hi, sir. Sir, I just wanted to ask, how many examples have you done?
Third one. It's the third one.
When did you, so you started what time, sir? Because I've been waiting for the link since 10:30 and I'm only getting it now.
No, but like, hey, Mr. Mantambo, you should know where Blackboard is when we started the link. Let me just quickly see.
I've never known the way to go through tools to find a link. It's my first time hearing of it.
What? Do you know how far we're in? And Mr. Kifo was telling me just now. When was the link even shared?
Sorry?
I'm just looking.
It wasn't shared on thing, because usually I find it either in announcements or the class group.
But it was like, but I mean, but you saw the announcement that we're having lectures at 10:30. So
Yeah,
no,
that's why I
people,
asked in the group, sir. I asked in the group
Yeah.
about the link and nothing.
Yeah,
But
well,
okay,
I mean,
it's
it is what it is now, you know. But people
So
are here.
which example, sir?
I think,
16.59.
yeah. Yeah, 16.5. Yeah. Mr. Kifo has nicely.
Okay.
Yeah.
Thanks.
Yeah, you should know I'm relatively on time, so I'm normally here. So if I say I'll be there, unless something's very critical. Okay, guys. So is there any questions on this before we move on? Like I said, we probably gonna have a lunch at past. Thank you, Mr. Romanus. I appreciate it. The man is feeling sick, but he's always showing up. He's a legend. He's an S4 legend. He's gonna go down as a big S4 legend. Anyone else? No questions, guys. It is what it is. This is like a simple. I don't know what more to say. Said, oh please. Mr. Mataso is also quiet. He's keeping it silent nowadays. Yeah. So we'll take it a step further. But again, guys, practice with me while we're doing examples. We have enough time. I made sure that we cover energy systems in one big shot, but you have more than enough skill when you walk out of this lecture. Likewise with transmission lines. Okay, so I think what we're gonna do now, but like I said, your core focus for test 2, know these things. That's what I'm doing now. This multi-cylinder stuff, make it your bread and butter. Do 1 or 2 examples. Take an example and just do it by yourself, right? Change some values if you need. Let's do the next one, right? So we're still staying in the flywheel domain. So we are here. All the same, and we're going to deliberately do another example. It'll probably be the last of this of its kind. We are example 16.5, and we're going to do example 22.2. This is in a separate note, but it's similar to example. Deliberately, obviously, I'm giving it to you. It's from a flywheel note. You'll see it yourself. Yeah, but anyway, don't need to worry about it. But again, as you can see, we got a diagram plus 410 plus 25 plus the, you will be expected to draw this, so I'm happy with that. And then afterwards we're gonna look at the last flywheel design, and then we have then what I might do, I might have branch off to the advanced examples, or I'll probably start off with a 4-stroke. My plan is probably do the 4-stroke next. I'll probably do the 4-stroke example 8 and example 9. And then I can probably come to the so-called more advanced examples, and then basically be done. So it's again all the same process really. So yeah, it's not difficult. The concept is, as long as you understand what you're trying to achieve here, obviously you can see it's the same, but the philosophy is you're just finding the flywheel, right? The size of the flywheel. Because when you build an engine, and obviously we're still doing multi-cylinders, but we will come to a part where we're going to look at the 4-stroke engine, and that's a different kind of, because the diagram is different, therefore we need to obviously look at it differently. So this one, Mr. Matambo, try to catch up. I'm going to give you guys maybe I should give you guys 5 minutes was enough. I think 5 odd minutes, just to at least get the start. So I'm deliberately letting you do it by yourself first, and then obviously I'll take it from there. After this, I'll probably get into the, like I said, maybe do the 4-stroke immediately, because obviously you guys can figure out the stuff in between. Yeah. Okay, so 10-2. Let's just work as fast as we can. 10-2. We'll do this example so we can have a lunch, and then obviously return for part 3, so to say. Yeah, part 3 after lunch, and then we can just conclude by 3 o'clock for the latest. Okay, thanks. Students, I highly urge you, please use this time to practice. So Matambo, Ms. Jack, we'll have Mr. Siam as well, so I'm a bit late. Mr. Shangeni, use this to practice. So this it's the same procedure. The only difference is you can see the one now, the mass and cross section, and obviously from the cross section, I did talk about the rim, and you can actually just find that. Yeah. So neglect the effect of the arms basically. So please sketch the diagram for me as well. Yeah. All right, I'm back. Yeah, Mr. Manus got the answer. Let me see if that's correct. I didn't solve this one. Example, what's it? 22.2. Did you give us the mass? The mass is correct. And obviously, you still have to find the area. Yeah, so we're gonna do this one, and then we will come back and then complete. We'll do the 4-stroke. My plan is to do the 4-stroke and then probably 2 advanced examples. Yeah, so yeah, we're getting there. We're getting there. We're getting there. Just be patient. Okay, so let's quickly solve this guy. Sketch is key, right? So I hope you guys got that sketch done. And the sketch should have looked like this. I've posted this note from the machine design textbook. So yeah, right. So if you don't know how to do the sketch, I'll just tell you again for the last time. Minus 35 goes below from A to B, plus 410, minus 25. Like I said, these values can just change completely. And obviously you can see it goes to L. So it's a bit of a long one over here. All right. So did everyone manage to get the total? Maybe I shouldn't even just do that because it's like a waste of time. So what is my max energy? Instead of me just doing this, because obviously we will have experience, it'll be a waste. Yeah, what's my max energy? You could have figured that out yourself. Max energy and 1 energy. Do you guys get the here? Just looking at the timing. I don't want to. I'm not sure what Mr. Dole is saying there. Typically it's E minus something. Oh, you're saying that you gave me the fluctuation of energy. So the maximum energy is E plus 415. Yes, thank you, Mr. Dole. That's perfect. E plus 415. If you got this, fantastic. And the minimum is definitely E minus 35. So you can deliberately see, like I left these chapters. Yeah, you can manage to actually get them. So anyway, you get this from a diagram. This has a lot of points. So I mean, this diagram will have obviously more marks. So if I look at it, maybe a table, it'd be like 1, 2, 3, 4, 5, 6, 7, 8, 9, like 9 marks to find the energy at all the points. And obviously find the maximum minimum energy. So now, guys, what we need to do is find the coefficient part now already. Yeah, which is the maximum energy minus the minimum energy, right? And obviously we're going to take E plus 415 minus E minus 35. All right, these will cancel and you'll end up with a value, and that value should be was it 450, right? Okay, plus 450 millimeters squared, as you're aware. And obviously we have to convert this into joules, so we take 450. Nice and easy, guys. Where is it now? Times 70 and 4.5 degrees. And the reason why we do this so we can get it into joules, not 2 pi over 180. And still the same thing, but now we can just get into joules. And I think Mr. Dole is 2474, right? 2474 joules. 2474 joules. Makes sense to me. So it's a long setup over here. So once you have that, you have to revert to this model, which is that omega squared. I think I'll just say I rather, omega squared and CS. Obviously I we can expand upon. I is m radius of gyration squared. They want the mass first, right? So they give the mass, and they want the and with having a mean mass. Okay, so how are we going to get this now, right? So again, just to further set this up, this is mass radius of gyration squared omega squared CS. So I'm assuming the radius, what is the radius again? Yeah, we have to use that radius. Oh, that's what I mean. So the radius, or they give us the diameter over there, right? So then we can compute the mass. What I'm just checking now is our, it's bothering me a bit now. I'm just having a look at it. What is our coefficient fluctuation of speed? So this is what is worrying me. It wasn't like the plus minus thing now. But Mr. Manage, you managed to get the mass, so I was confused there. So it says it's 2%. Not we say 2% of the mean speed. Oh, it is 2, so it's 2%, right? That's 2% as is, which is supposed to be. Yeah, that's correct. Yeah. Okay, now just looking sure. And then we're going to take 2474. Okay, let me just say this will equal mass. CS was, okay, radius is 650, 0.65 divided by 2 squared. Omega was typically given, it's 900 RPM squared, and our CS is just simply 0.02. And if you work that out, 2474, 0.65 divided by 2, 900 times 2 pi over 60 squared times 0.02. What mass do you get for your flywheel? It doesn't seem like I'm getting my answer here. Not sure exactly what I did wrong. Oh, it's a radius squared, that's why. Okay. Yeah. 131.84. Students, are you still there?
Yeah, sir, I'm a bit confused on your R. You got 0.65 over 2.
Isn't that the mean diameter?
Just
So that's the diameter. So you need radius.
okay, thank you.
Yeah. I equals mass R squared. Yeah. I don't know why they didn't say radial gyration, but yeah. Anyway, it's not going to be really complicated. So once you find the mass is equal to density times volume, right? Obviously, density is density, but I made you aware, and obviously volume. Let me head back now. Let me just quickly show you. Okay, and I mean head back. This is what I'm referring back to the slides. Is when we get into the more for the particulars. Mr. Doyle, your mic, please.
Sorry.
Yep, it's cool. Remember when I mentioned the mass of the flywheel, and the area is going to be breadth times thickness, right? So that's what we're looking at. So it's 2 pi r or pi d times a times rho, but a is going to be b times t. So I hope you guys got that. So remember, the reason why we look at that is because most of the energy is anyway stored in the rim and not in the hub itself, or the so-called boss and the spokes, so to say. All right, so we got that area, and then heading back. So it's going to be expanding upon this. What was it again? Pi d, and the area was, and obviously this is area, and it is now b times t, and that's the mass. So 131.84. Our density is given 7,200 in this case, right? You times it by pi. So easy, right? What is d again? 0.65. That was supposed to be a t here, right? I don't know why it doesn't look like a t. So let's just quickly leave that as is. Obviously, this will give me the area, which is this. Delete. So I'm just finding the area first. Okay. So I'm just organizing that area. What area do you get? Okay. I think you should get 8,967 1 times 10 to the power negative 3. And remember, area is B times T, which is the breadth and thickness of your rim. But they stated here that your rim is rectangular and the width is 2 times the thickness. Your width is 2 times the thickness. So B, we just basically replace there and we end up with 2t squared. We substitute, obviously, that there. Right, that's a typical thing which they give. That's 8,976, 1 times 10 to the power negative 3, divided by 2 in the root, and then we can find our thickness of our rim. So Matoso, are you following? And I think my thickness of my rim should be 67 millimeters. You guys get that? And obviously my breadth will be 2 times that. That'll be around 134. This question could be easy around 20 odd marks. 20 marks. Any questions, students, before we go on our lunch? Any questions to find the area? Do you know what the area is? It's pi d. Thank you, Mr. Minus. It's not, guys, this is not particularly difficult. I've tried to make it as easy as possible. Yeah. Thank you, Mr. Kifa. And you have enough practice problems to go through. Just go have a look at it. Like I said,
yeah, so I understand. Yeah. I understand the process. I just have a small question on the your volume there. It's pi db, pi times depth times pi times diameter times breadth times thickness, right?
Yeah. So pi d, that's the one. That's your circumference. That's b. That's another meter. That's t. That's another meter. So obviously times all of this. That's meters cubed. You times by rho, which is what, kilogram meter. Yeah, you know. And obviously that's mass. So this is your C.
Right. Yeah, no, it's just the pi d. It's not pi r squared or pi d squared over 4 because it's the circumference we're looking at.
Yes, it's either 2 pi r or pi d. It's entirely up to you. Yeah, same thing. 2 times r is d. Yeah.
Yeah, no. I was just thinking like no, hold. I was just thinking of area for it, not circumference. Okay, no problem. Thank you.
Yeah, it's basically the that's fine. If I had the actual flywheel, you know, I think what I'm trying to say, can I sketch this whole thing? Can I manage? What we're looking at is this portion here, like you know when you touch your tire, that whole piece there, that the pi d component is this over here. That's the circumference, obviously, yeah, and then it's width and breadth or whatever, thickness. So yeah, it's the rim is essentially the main. Okay, guys, let's come back at 2 o'clock. Have a good lunch. Don't eat too heavy. Obviously, we have a few problems to do. I'm hoping we have around four problems to knock out, and then we're on our way. But what we've done now is good preparation for your test 2. I think for part 3 would be more like on the final level. So for test 2, make sure you prepare everything till now, right? Till part 2, so to say. And part 3 of the lecture would be obviously all the advanced problems. Not advanced, it's still doable, but you know what I mean. Your scope, so to say, it's not fair for me to give you everything to do for test 2. So yeah, okay. I'll just close